And when that happens, we end up with a fault. And faults in this case, we can describe just like we did when we were talking about looking at the fold. We can use the same coordinate system to describe the orientation of faults, and that's strike and dip. Remember, we use a horizontal plane as kind of our standard to compare to. And then we take a strike, which is simply how that fault plane cuts along that horizontal plane. So I just get my compass absolutely level with a little bubble level in the compass, put it up next to the rock, and whatever that compass bearing was, that's my strike. It tells me the kind of the long axis direction. And then I need to measure the angle that it's dipping into the ground. And again, I use a little inclinometer, and I measure that off of the horizontal plane. My instrument has a little level bubble in it to tell me where that plane is and what to measure.
What does strike do necessarily?
Okay, strike would be this line right here. So strike's going to tell me kind of how this thing is oriented across the map. Dip is going to tell me how it dips into the surface.
Okay.
And those are the only two measurements I'm going to need to tell you how this thing's oriented. Yes, sir.
Does that account for like bends in the folds?
Mm-hmm. Yeah, I can do the same thing with a fold. Obviously, as something noses around, the strike and dip is going to change, isn't it? I mean, here at the very end of the nose, I'd have a strike that's running across this way. On the edges, my strike would be this way. So as I put those strike and dips on my map, I just kind of be able to connect them along, and I know the exact shape of the structure. As the structure gets more complex, more strike and dips to get the details.
So just take more measurements?
Yeah, just take more measurements, yeah, exactly. And that's always one of the issues. Can you take enough that is enough exposed that you can get enough measurements, or do you have to just kind of wing it with a few measurements and connect the dots and do the best you can? You know, it's always part of the science and the interpretation. Good question. Okay, so we looked at our faults, defined the fault plane, the down drop block, the upthrown block, and we also talked about last time that we can use a couple of other terms for the upthrown and down blocks. For the down thrown block, we would use the hanging wall block. For the upthrown block, we'd use the footwall block. And we get that from mining terminology. The footwall block's the one you stand on, the hanging wall block's the one you hang the lantern on. Now, I said you'd use that for upthrown or downthrown, but is that always the case? And this is why we do footwall versus hanging wall. It works in this case. You can see here I'm starting out with flatline rocks, just like I'm supposed to with my stratigraphic laws. We've got a fault, and here is my downthrown block as it's moving down. You can see the offset from one layer to the next. So this is my downthrown block, there's my upthrown block. And in this case, it works just fine. This is what we call a normal fault. In this case, the hanging wall block here, if I did my little tunnel here, this would be where I'd hang my lantern. It would be the one that I'd be stepping on, the footwall block. So in a normal fault, we see the hanging wall block moves down in relation to the footwall block. So you can see that the length of this block has extended. It's gotten bigger. As I allowed that block to slide down, means it's expanding this way. So what kind of stress am I looking at here? Pulling it apart. Tensional stress, isn't it? So I'm expanding the crustal section laterally, getting bigger. So that works for a normal, everyday, normal fault. And here, you can kind of see, we've got a normal fault. This layer right here used to be connected to that layer here. Here's the fault coming through here. This block is dropped down compared to that block. So there's my hanging wall block, there's my foot wall block. Okay? And what we see is a very typical style of topography, of mountain range that gets developed this way. And it's what we call HORST and GRABEN topography. The HORST is this area that stays high as the mountain range. The GRABEN is the area that drops down like a big keystone fault making the valley. So notice the faults. This is a normal fault here. This is a normal fault. The yellow has dropped down, the yellow dropped down. Here's my foot wall, hanging wall, foot wall, hanging wall. Normal faults. So if I'm going to make this kind of topographic expression through this normal faulting, this whole area has to be kind of pulled apart, doesn't it? This wider top part now is slipping downward into a smaller area. I've got to pull that area apart to allow that keystone to drop. So, typical extensional terrain development. And this HORST and GRABEN area, Death Valley is one of these. It is a big GRABEN here, and Death Valley is basically 384 feet below sea level. So if the ocean were to connect, that would be a big flooded part of the ocean, but it's isolated in the ocean. If I look at the southwest part of the United States, you can just see kind of one ridge after another. The highs are the HORSTs, the valleys are the GRABENs. This whole part, you see, all the way through California and the Great Valley, all the way up through Nevada, Arizona, Mexico, up into actual parts of Oregon and Idaho. All of this is HORST and GRABEN topography. And you can see here, things are running this way, grain is this way, so you know it had to pull apart east to west. It had to extend this way to allow those valleys to drop and those HORSTs to stay high. So very typical, normal fault type of topography. So, HORST and GRABEN landscapes are developed by a series of normal faults. I'm wondering you get 10 seconds because you all know the answer. Okay. Everybody says true, except for 4 people that are probably going to need to do a little extra study. Okay. Yeah. This is the whole thing. Normal faults. We're going to extend the section laterally, and that way we can let these keystones drop down. Okay. Well, what happens if instead of that hanging wall dropping down, it goes up? Same fault, just the opposite movement along the fault. Now, the hanging wall is moving upward. I mean, I can still figure out this little deal of hanging wall versus foot wall with my tunnel, can't I? Obviously, the hanging wall and the up-thrown block and the down-thrown block just reversed, didn't they? But the relationship of foot wall to hanging wall is still the same. So that's why we tend not to use up-thrown, down-thrown blocks. We tend to use hanging wall, foot wall blocks, because that relationship remains the same regardless of the direction of motion along the fault. Okay, so instead of a normal fault where the hanging wall would have dropped down, instead the hanging wall goes up on the fault. So what would be a really good name for this? Reverse fault. It's just the reverse of normal, isn't it? So a reverse fault now, the hanging wall block is going up. special cases here. That works as long as I'm at 45 degrees. But what happens if it's a really shallow angle? Instead of being 45 degrees, it's more like this, it's more flat. Now, if I've got a reverse fault, this block is going to start moving up over the footwall block, isn't it? And notice what I'm doing. Instead of just kind of moving them this way, I'm moving it more laterally. Once I hit 45 degrees, there's more lateral displacement than vertical displacement. So now I am really shortening up the section, aren't I? I mean, I'm just compressing it like this, stacking it up in slivers. So when we have a situation where the reverse fault is flatter or shallower than 45 degrees, we call it a thrust fault, because that rock is being thrust out of the basin on top of the surrounding rock. It's kind of a specialized reverse fault. 45 degrees is the magic number. So 45 degrees is kind of important to remember, because right now we're talking about fault motion that's all along dip. Right? Dip is that angle into the ground, and all this motion is back and forth, whether it's up thrown or down thrown, it's moving along that dip angle. So we call this whole classification of normal, reverse, and thrust faults, we call them dip-slip faults. Okay? I mean, it's just kind of, you know, basic common sense terminology. Now, here's a thrust fault that is gigantic. It's a big, huge thrust fault. You can see it here in the schematic where this limestone has been thrust up over this shape. And in this picture, you can see it from the air. Here's the limestone back here in gray. That's all of this. And this browner color is all of this in here. And then down here, you get some sandstones. And you see that down in here. So all of this gray is basically being thrust toward the right in this picture, overriding the shale and sandstones. This is the big fault that runs just to the west of Las Vegas. It's in the Red Rocks area. So you go out to Las Vegas and you kind of see this valley. Well, this makes up the west edge of that valley system. It's this big giant thrust moving toward Las Vegas. Here's one. It's out in Glacier National Park, and it's actually left a mountain out there, Chief Mountain. What's happened is, here's our original flatline rock, and we have some Cretaceous rocks sitting on top of some Precambrian rocks. So that means Cretaceous rocks, about 65 million years ago is when Cretaceous ended. Precambrian ended about 560 million years ago. Big unconformity between there. But now we've added an even more complex problem. We've put a fault in here, and we're starting to compress this section. And now this section to the left of our fault is starting to move along that fault zone and get pushed up over its neighboring block. And look what's happening. I've got Precambrian aged rocks here that are now being pushed and slid on top of Cretaceous aged rocks. So look at the result. I've got a column of rock that's out of order age-wise. I've got Precambrian up to Cretaceous, and then it repeats Precambrian, Cretaceous. Man, that can be a little confusing. And then you throw in a little bit of erosion, and out of this whole thrust that we've seen here, just a little piece of Precambrian sits out here on top of Cretaceous rocks, and that's Chief Mountain. So your immediate reaction would be, oh, look, this must be like a volcanic neck, or it must be some piece of volcanism that's come up through the section, and I've got this sitting here. Well, then you find out it's Precambrian, and you kind of go, that's kind of hard to have Precambrian, you know, cutting up through Cretaceous stuff. The age doesn't work, right? You gotta have the older stuff there first. So then you start looking at the mountains and the fault systems. And it's this big, what we call the Lewis overthrust through there that's made that mountain system now, the eroded remnants of the thrust, and just this one little chunk of section that's left out there, Chief Mountain. Pretty amazing. This is about a 10-mile section here between the range front and Chief Mountain. That's about a 10-mile track. So you can imagine the amount of rock that is being thrust out over this other rock unit for that kind of distance. It is an incredible amount of energy involved in all this. Okay, true or false? Although classified as vertical or dip-slip faults, thrust faults often have much more horizontal displacement than vertical displacement. 20 seconds on this. Okay. See how we did. Yeah, okay. Get everybody got it there. Yeah. Whether it's a reverse fault or a normal fault, it's moving along dip, isn't it? It's moving along that angle that's dipping into the ground. So all we've done now with the thrust fault is we've exceeded 45 degrees. We've really shallowed that dip out. So now 45 degrees would be equal, wouldn't it? I'd have as much vertical motion as horizontal motion. But once I get past 45 degrees, I get way more horizontal motion, lateral motion, than I do vertical motion. Yes, sir?
What's causing the stress force, and like, is it always constant, or?
The stress force probably is not constant. That's probably always changing. And right now, with this type of stress, compressive stress, we're probably talking plate tectonics, two plate edges crashing together. We're talking major regional plate tectonics here.
What causes it to be at such a shallow angle?
Yeah, what causes the angle? Yeah, that's a good question. It's probably a number of things. It may be just as simple as how things are stacked horizontally and the weaknesses in the rock. If we've got one rock that's particularly weak, that may take the fracture that's cutting through the units and take it off along that weaker bed. So that's a possibility. It may be pre-existing jointing. Every case is kind of unique, and you've got to kind of look at it and figure out what the cause was. But you get out in the Rocky Mountains and you see a lot of this kind of stuff. It's pretty typical. There's a whole section of the Rocky Mountains along Denver that they call the overthrust belt, and that's what's going on. These rocks are sliding out to the shallow angle. Okay. Cool. Okay, so we've been talking about dip-slip faults, moving along that angle. What if instead of moving that direction, they move along strike? Okay, now I'm just moving laterally, side to side, along that compass bearing that we took. And as you might guess, we call these strike-slip faults. So right away, you've got this idea that dip-slip faults are moving kind of more up and down, even with a thrust, it's kind of a up and down motion, versus strike-slip faults that are moving side to side laterally. And these are the faults that you think of when you think in terms of the San Andreas fault, you think in terms of what's going on in California. One of the things you look for when you see these strike-slip faults is there's got to be a line in the ground, right? That things are, one block's moving past the other block. So I would look for offsets. Here's a river that was coming along, oh, hit the fault. Well, there's where the river